Okay, hello team. I think we need to pull up the homework assignment here and talk about it some more. You can turn that homework in next week. It'll be good to have it by Tuesday, Wednesday, something like that. If you've already turned it in and you're happy with it, that's fine, just let it go. If you've already, I think a couple people have already submitted and you want to make changes, just make whatever changes and submit again, and I'll grade your final submission. So don't worry about that. But I know there's lots of questions. There's some open-ended stuff in here, and I can't really discuss it with you until I get you involved with it. And I can't get you involved with it until I give you a due date. And so I think I have most of you involved with it, at least right now, which is a step in the right direction. So let me pull this thing up and let's talk about it some. That's just an email list. That's not what we want. Here we go. And make it a little bigger. Okay, so let's just go kind of slowly through this thing. I'm not going to reread it all because I think you guys are probably pretty much up, probably more up to speed on it than I am as far as the given information. You know, we operate all the time. We got 400 PSIG saturated steam. So the high pressure steam that's what's coming out of the boiler. And so if you need a steam temperature, it's saturated steam at 400. And it's usually good to round up to the nearest tenth or something, because if you give it too low, the program kind of doesn't like it. But anyway, basically the saturated temperature of 400 PSIG steam is the boiler steam temperature. Process uses and other headers. I don't think you should have any questions on that. Annual electrical consumption, 83,000 megawatt hours. That lets you calculate the average load on the plant to put in as the average load on the plant. So we're burning natural gas, 350 a million BTUs, water cost, flue gas, initial stack temperature 525, pretty high, and oxygen 8.1, no CO, so at least we're burning the fuel. Ambient temperature is 85, so you've got all the information you need to calculate a stack loss. And your boiler efficiency really should be 100% minus the stack loss, minus an estimated shell loss, which is probably on the order of 0.5%, certainly not more than 1%. But, you know, I'll let you estimate that based on we had a little information in the slides about estimating shell loss. You have the chloride concentrations, so you can calculate the blowdown rate. DA pressure 12. Steam trap population on the high pressure system 15, medium pressure 30, low pressure 50. And so, you know, every year, you know, you start out with this number. And so 5 years ago, you could assume they were all working. So after that first year, then 2% of them failed. Okay, so then you have a certain number working and a certain number failed. After the second year, another 2% of those that were working failed. So then you have additional failures, and you just work through the years until you figure out how many you think currently have failed because they haven't repaired any in 5 years. Okay, and then you're going to go out and repair them and try to save them some money. Assume that failed trap's blowing live steam and the condensate return system is at atmospheric pressure. So you have to estimate that vent rate. We got some stuff in the slides today to help you do that. That steam system survey guide, I think chapter 5 or chapter 6 has some stuff in there on estimating leaks as well. I gave you an orifice size that will key that calculation for you, or you can find leak tables that you can use as well. Currently, there are no turbines. You're going to investigate that. Boiler capacity is 250,000 pounds an hour, and it would be possible to raise steam pressure. That's something you could think about in terms of turbines. I mean, I have recommended that before. If somebody's got a turbine, or if I want to put in a turbine, well, maybe I can't do superheat because I would have to change the boiler. But if all I have to do is increase the settings on the boiler, maybe replace some safety valves, then I could operate it. Probably wouldn't go clear to 600. Maybe you go 550, something like that. Give you, not push it clear to the top. That might help you on your turbines. Something to think about. Condensate return percentages, that's just plug in numbers. Condensate is returned to an atmospheric condensate return tank at 240. The measure tool can't simulate that. So you're going to have to do some hand calculations when you get to that. You're going to have to calculate the amount of flash steam. Well, that's not hard. You can do, or you can get online. You can find flash steam calculators that'll do it for you. But it's pretty simple thermodynamic calculation. Your DA vent steam is 2,000. Well, you have to put in a percent rate, and then you look in the model, and the model shows you how much steam is being vented from the DA. Well, if it's not 2,000, then you got to guess another percent. You go back and forth 3 or 4 times, and you can come up with the correct percent that gives you, in your base model, 2,000 pounds an hour. Steam is supplied, medium low pressure through PRVs. We're not spraying. Information on the Boiler Combustion Air Fan, 125 horsepower motor, and we took some measurements on it, that sort of thing. So you can calculate the current energy consumption.
The AB, AC, BC, what are those referring to?
Well, that's how those measurements are taken. If you go in with a voltmeter, the voltages you want, so you can take measurements from the phase to the neutral or ground, and you get like 277 or something. If you take these are phase-to-phase measurements. So VAB is the voltage touching your 2 leads to phase A and phase B. So that's how you have 3 measurements you have to take. You take the measurements between A and B, A and C, and B and C. Those are your 3 voltages, and then you average those voltages together to get the one that you use in the calculation. Likewise, you add up all those currents and you divide by 3, and that's the average current. You use the square root of 3, and you have to estimate a power factor. Power factor for this is probably going to be on the order of between 0.8 to 0.85, something like that. And then that will let you calculate the kW of input power to the motor. You got a motor efficiency, you can go out there and look around. It's probably someplace between 90 and 95% on a big motor. Okay. Steam leaks are minimal, so there's no real other opportunities there other than to the repair of the steam traps. There are no opportunities identified further. All right, let's go down. So, areas to investigate. Like we did in class with the stack loss, first assume that we tune the boiler with 8.1% goes to 5%. Then you can change your boiler efficiency and run a project, run a scenario, change your boiler efficiency, look and see what the savings are. They say that costs $5,000. You do your payback and your internal rate of return. Next, assume the boiler has already been tuned. We want to look at installing the automatic combustion control system. So we would assume for B that we've already done the tuning. And so then the base case on B should be 5% oxygen. And then we're going to take it to 2% because we're going to upgrade the control system. So you're going to have to change your base case to run that. And the cost is $100,000. Then for C, assume that, you know, we're not sure if we're going to buy the control system. So we're going to base C on 5% on the base case. But investigate the installation of standard feed water economizer to preheat feed water before it enters the boiler. So what you do then is you keep the oxygen at 5% for both cases. You have the elevated temperature on the base case, and then you reduce the stack temperature to 275 at 5%. You get an improvement in boiler efficiency, and you run that in the model. And that's an expensive project, $400,000 or $500,000. Calculate a payback, and you know, once you start doing this in measure, hopefully it gets easier. And then case D, just assume that we did it all. You can go back to the original base case, say we tuned it, we put in automatic controls, and we put in the economizer. And so that's going to cost, you know, say $500,000 for all that. What's that look like? Okay, reduce blowdown loss. So now on this one, I would probably go back to the base case. If you want to go back to the 5% case, I mean, I don't care. You know, either the very starting case or just after tuning. You know, you could do either one. I'll run both of them to compare this to. And basically, these are options you can turn on the inputs. You can flash the steam to recover the flash steam, turn it on. You can turn that off, then you can put in the heat exchanger, and then you can turn it, and then you can turn them both on and run all three of them and see what impact the flash tank has by itself, what impact the heat exchanger has by itself, and what impact they both have together. And kind of look and see what the economics of that would look like. You got some cost. Okay, cogen, you can start adding some turbines. And let's see, so we're going to say that the cost to install a turbine is $1,500 per kW, and you have to look on the model and see how many kW you're going to get out. And most of the time for the costing, we would round up to the next round size. You know, if it was making 763 kW, I might round it up to 775 or 800 as far as costing of the thing. Because you probably can't buy 763 kW, you know, you're going to get a bigger one, and then you're going to get whatever you get out of it based on exactly how much steam goes through it. And go ahead and just use an isentropic efficiency of 55%. That's a good ballpark number. So investigate the installation of a back pressure turbine generator set that operates between the high pressure and medium pressure headers. And then you look on the model, see how much power you're getting out. That lets you do a rough estimate of cost, and you can do then a payback and an IRR. Investigate installation of a medium pressure to low pressure back pressure turbine. So you can turn off the first one, turn on the second one. Again, investigate the installation of both turbines together. And then, yeah, on D, I forgot I had actually included this. Go ahead and increase the boiler pressure to 600 saturated steam and rerun case C. So you'll have a different base case. So you'll have to go back and establish a base case at 600 and then compare it to, well, if it will let you, I'm not sure if it will let you increase the boiler pressure in the model. I mean, on a project, you may have to increase it in the base case. I'm not sure. If you can just increase it in the in running the turbines, then you go ahead and just do that and leave it 400 in the base case. I can't remember. I haven't gone back and rerun that this year. I've run it before, but so anyway, the cost of, and that's an extra 30,000 to modify. You would have to replace your safeties and maybe some of your control valves that wouldn't operate at the higher pressures. Steam trap. Okay. Assume the steam loss rate from the failed traps can be reduced by 75%. So you've got a certain number of traps. You're going to estimate, based on your pressure and your orifice size, how much steam is leaking from each trap. And then you're going to assume that if we go out and do a project, that over time we can achieve savings of 75%, because as soon as you go fix them all, 2 weeks later, three more have failed. You know, it's the way it is. So you can't, it's not realistic to assume that you can save all of that, because they're going to keep failing and you're going to have to keep looking, and it's a long-term, it's a management situation. Find them, fix them, find them, fix them. Okay, VSD on the boiler combustion air fan. I'm going to talk more about that in some detail. So VFD losses estimate 3% of full motor power, but I'll come back to 6 here in a minute. And reduce the DA vent steam to a typical value. Measure has a suggested range. And one student indicated he took the middle of that range, you know, as an estimate of what it could be reduced to. I think that's wonderful. I think that's very good, because y'all don't have a lot of experience in this, but the tool gives you some guidance. Just accept what they give you. That's fine. Okay, and then the rest of it is just putting your stuff together. Okay, so let me show you some stuff on this fan thing. And I can email out some of this to you. So these are some curves. This is data that came from a study that was done by the National NREL, National Energy, Federal Energy Lab. What's NREL stand for? I can't remember now, but I've got a copy of it. You know what I may do is email you out the study as well, so you can have this. But anyway, these are their numbers. They did a bunch of testing on some fans, and they're comparing here. They're comparing different fan control technologies. You know, so one of them would be a discharge damper. Let me see. Let me, I didn't hope, let me pull up a fan presentation here real quick, so I can show you pictures of some of this. Presentation. Fans. Okay, well, this is this shows a fan, a centrifugal type fan, and I've got some better pictures here. I'll show you in a minute, but this kind of illustrates. So these outlet or discharge dampers are just, they're either opposed flow or parallel flow, and they could be horizontal or vertical, and they basically are in the ductwork or strapped on pretty close to the discharge of this fan, and they simply close off. And when they close off, it adds resistance to the system, and so it reduces the amount of air airflow, but the fan is still turning and it drives the discharge pressure up, and they work in terms of reducing the airflow, but they're terribly inefficient, okay? So they're not very good at all. Then the other technology, this is what we call an inlet guide vane. And I went too far. That's the same picture from a different side. But basically, the air is being sucked in. This is the inlet to a centrifugal fan. And this is pulley belt driven. The motor's down here, and we're turning it with the belts and all that sort of thing. The fan wheels in here spinning. So what these things, these are kind of like these little pie-shaped dampers, and they're all hooked together on a rim, and they've got a mechanical linkage. So if you want more airflow, you open these up and they just become, you know, kind of parallel, and the air coming in just hits the side of the blade, and so you get the maximum out of the fan you can. If you want less, you start kind of turning these things sideways, and they all turn together. And what they do is they impart a pre-rotation to the air and get it pre-rotating in the same direction that the fan wheel is turning. And that reduces the impact and the efficacy of the fan wheel, and so you get less air out. And so this is a fundamentally different technology than the discharge dampers or the outlet dampers. And this is a little more efficient. Okay, let's see here. This is some stuff from DOE in some of their literature. And so they're showing the efficiency of different ways to reduce the capacity of a fan. Most of these are for a centrifugal fan. This variable pitch blade, it would be for an axial fan. But you see, I mean, and I put these dots on here. I just said, for example, what if you're trying to get 60% capacity? Well, you can see at 60% capacity, if you're doing speed control, which would be the variable frequency drive, you're down here someplace, you're less than 40% power, okay? If you're on inlet guide vanes, you're what, 45, maybe not quite 50% power. So they're not as good as the speed control, but they're not terrible. And if you're on discharge dampers or outlet vanes, is what they're calling them here, look at this, you're way up here. So if you're controlling a fan with these dampers, and you can put a VFD on it, or you could even put inlet guide vanes on it. If you spend a lot of time at reduced flows, you save a ton of money, okay? So that's what this is trying to get at. So now let me look at this Excel sheet with this data. So this is a bunch of data, and I just copied it out of the paper, but then I plotted it out. Yeah, let's see here. Get rid of it. Yeah, I'll never figure out how to bring it back down, but that's all right. We'll figure it out. Okay. So if you look at this curve, so I just curve fit. I put their data points in and I curve fit it, and I've even got equations for this sort of thing. For the fans that they tested, I got a curve like this for discharge dampers. I got a curve like this for inlet guide vanes, and I got a curve like this for speed control with a VFD. That's pretty compelling, isn't it? If you're running 60%, you know, that number's a little bit off, but, you know, it's what, 22, 23%. Up here, I'm about 60%. And up here, I'm about 84, 85% power. Wow, what a good project. And so that's what I want you guys to investigate. Okay. Now, there's really a lot of meat on this bone, if you think about it. Now, let's see, where do we want to go? So, you have a model that tells you how much steam you need to produce. You got all kinds of models. You know, you can pick the base case model. I don't care. I guess you could base it on, you know, when you first walked up to the boiler. That's fine. And I don't remember what the number is. It's 150, 170, 175,000 pounds an hour, or something like that. On a, let's just say it's 175,000 pounds an hour. Okay. Well, the capacity of this boiler is what? 250,000 pounds an hour, right? So if you're making 175 divided by 250, you're running at 70% load. So if you're at 70% load, you probably need someplace on the order of 70% of the rated capacity of the fan, right? I mean, it would make sense because the fan has to be big enough to operate at 250,000 pounds, or you got screwed when you bought the boiler, right? They didn't sell you a big enough fan. So at least that, and experience would tell us that that fan is probably oversized, because the last thing a boiler supplier wants is to supply a big boiler that's, you know, $5 million and put a fan on it that's too small for it to operate at full capacity. That's like buying your new Corvette and looking under the hood and you got a 4-cylinder engine and you're going, holy moly, something wrong here, man. I can't go over 80. I'm supposed to be able to go, you know, 175 in this thing. You know, I mean, you don't want to undersize a fan. So the reality of it is you probably have enough fan to go 275 or 300,000 pounds. But anyway, that's I guess neither here. That's just a side comment. But so, I mean, if you just ratio the steam flows, you would say at 70%. So then that would mean that my fan would be operating at roughly 70%. And this is steady state, so it's 70% all of the time. Okay? Well, one thing that you can do is, you know, you can use these curves if you had them. But I guess I don't mind sharing them with you. But you could come in here and say, okay, well, so this is where if I'm at 70% flow, you come up and you say, well, that's right at 90%. So that says that I'm at 70% flow with discharge dampers. So that means that my percent full load power should be 90%. But you've got a measured power. So you know what that is. You could divide that by 0.9, and that would give you a projected 100% power. Or you could take the capacity of the motor to get your 100% power. You know, at full load, that fan is probably going to pull, you know, pretty close to 125 horsepower if that's the size motor that's on it. Okay, and then you have a measured case for here, and you can come down and you can pull a number off this and use that to estimate what the power would fall to if you put a VFD on there. And I told you to add a little 3% extra for drive losses, even though I think these numbers have drive losses in there, but just you'd rather be a little conservative. So that's one way to do it. The other way, you could go play around with this ABB. I haven't done this in a while. ABB Fan Calculator. You play around with this, you actually will learn some stuff. Get out of there. Yeah, be careful. I don't want that. Let's do it that way. Oh, that's not the one that takes you. Software tools, that's the one. I went to the wrong thing. Is that the one? Where's that one I had the other day? Ah, well, crap. Vfd savings calculator. Where's the ABB one? Calculator. It's not going to let me go to that thing. There we go. Didn't find the right link. Okay. Advanced. Well, let's see what we got here. Well, you know, country, that's pretty easy. Oh, God. You know, I hate them. They don't put the U.S. first. But anyway, I guess I shouldn't be that way. What? Where are we? What?
I couldn't even find the US on that list.
Well, I've used this before. Are we not on there?
I couldn't find it.
Really?
The US is in the top right-hand corner where it says like Euro.
Top. What?
The top right-hand corner of the screen.
Over here?
A bit above that, where it says Euro, metric, English.
Wow. Well, we sure don't want metric. Get out of that. All right. General, but we don't show up over here? That's weird. Oh, well. All right. System. Okay, now this is what I want to get to. All right, so if we wanted to try to work with this thing, what's our flow volume? How would we know, say, what the design flow was, or at 70% flow? How could we figure that out? Well, okay, so let's take a look at this. All right, so, and I can email you this. I mean, this information is readily available if you look for it. But we're burning natural gas, which is basically methane. This comes from the steam book, Babcock and Wilcox. So this column over here, or these columns, this is cubic foot of, say, O2, N2A, which is everything in air besides water vapor and oxygen, and air per cubic foot of combustible. Okay? Well, a cubic foot of natural gas is worth how many BTUs? The higher heating value. It's 1,000. A cubic foot of gas is 1,000 BTUs. Well, okay, a pound of steam, nominally to produce a pound of steam, how many BTUs? Nominally, it's 1,000. It's probably 850, 875 across the dome, and then you got to heat the feed water a little bit. So a swaggin, I mean, we can go figure it out, but a swaggin number is 1,000 BTUs per a pound of steam. Well, okay, so let's think about this. This thing, we got 250,000 pounds boiler capacity, 250,123, okay? And each pound would require what? 1,000 BTUs that actually goes into the steam. Okay, so times 1,000. So that's 250 million BTUs an hour. But our boiler is not 100% efficient, right? You've got an efficiency. I'm just going to swag it at 80%. So then I'll divide this by 0.8. So that's 312.5 million BTUs an hour. Okay. Now, and that's the heat input that I got to put in the natural gas, in the methane. Well, so each cubic foot is 1,000 BTUs, right? So if I divide this by 1,000, I'll get cubic foot of natural gas per hour. So I divide by 1, 2, 3. Okay, so that's 312,500 cubic foot per hour of gas. Well, we usually do airflows in terms of cubic foot per minute, so I'm going to divide by 60. So that's 5,208 cubic foot per minute of air. I'm sorry, no, of natural gas, the CFM of gas into the boiler to provide the heat that I need. Well, then I look at this chart up here, and it says to burn methane, I need 9.547 cubic foot of air per cubic foot of gas. Okay, so I'm going to multiply this, well, I'll store this one away, and I'm going to multiply it by times 9.54. Well, of course, I typed it wrong, but recall 1 times 3,1 times 9.547. Okay. So what is that? That's 49,724 cubic feet per minute. But that's for stoichiometric. This is stoichiometric. But we have excess air. And you know how much excess air because you have that stack loss calculator, right? That's in the measure tool. It tells you excess air. You put in oxygen, it'll tell you excess air, whatever, you can go back and forth. It depends which oxygen level you're going to run. If you're going to run 8.1%, well, I bet that's at least 50% excess air. I don't know, I'd have to check. But, so I can multiply, this is almost 50,000 CFM. If I'm 50% excess air, I got to multiply this by what? 1.5 times 1.5. Okay, so that's 74,600. So I'm gonna just, for playing around with this calculator, I'm gonna say I'm 75,000 CFM, okay? All right, so volume flow, CFM, 75,000. Okay, now we can look at this, and now the 12 inches of water pressure increase right now, that was left over from the last time I ran this thing, and the fan efficiency, 90%, I don't know, that's pretty good. Transmission efficiency, that would say it's probably direct drive, which could be. You know, if it's belted, you could put in a 3 or 4% belt loss. So you could put 0.97, 0.96 in there to account for a drive loss. Let's see. Okay. Flow control, outlet damper. Let's see, motor horsepower required, what is that? Say it's 172. Well, so that's what it's saying. Well, let me see, motor power. My motor power is 125. I can do that. But say it's still not happy. And so what that says is that my pressure, at least I have some justification for my 75,000. And I just guessed. I mean, 12 is what came up in the calculator. So I need to reduce this pressure until I get this required motor power to be, because this is a full load number. So I'd like that required motor power to be about 120, 125, something like that. Okay. Well, so let's try 8. 114, that's not bad. I could do, what if I do 9? 9's a little much. 8.5. Now, situation is, if I was actually working for a plant, I could take measurements on the fan. I could get the fan model number. I could take the rotational speed. I could call up the fan company. I could get on their website, get a fan curve for the fan. I could get the real information. That's a leap way too far for you guys to go on this homework. But I mean, that's how the game gets played out there in the real world. But you got to be able to produce some reasonable numbers, you know, pretty quick. So let's go on down. Okay, efficiency, class of motor, supply voltage, where this probably isn't going to make much difference, but Yeah, 480, 460, probably 480. Centrifugal is good. Probably not forward curve. Probably, yeah, let's see. What are they giving us here? Forward curve. Backward, probably, I'll go there. Annual running time, 8760. Duration. Okay, so this is where I'm going to put in the, I want a custom flow. So I'm going to run 70% all of the time. Got a bunch of zeros, don't I? But you can see where you can tailor your inputs for a particular situation. Energy price, what are we, 7 cents, I think? CO2 emissions, investment cost. 125,000, okay. There we go. So, with dampers, with VFD. You know, be interesting, and I may do that, pull the savings off of my curves and compare it to this and just see if they got the right answer. I'm going to be egotistical about it. They might have a different opinion of that. But anyway, so this gives you some kind of idea. You can find other calculators. I can email you this spreadsheet out so you can take a look at that. But that's what we're getting to. These discharge dampers are horribly inefficient. Now, the amount of energy used by that fan is minuscule compared to what's used by the boiler, but electrical energy is far more costly per unit than the gas. And this was a good saving. So, I mean, you know, every dollar's green. The plant wants to save every dollar they can. And if they can get, well, let's see, do we get a payback here? I can't remember. Well, there's direct payback. Okay, so 1761 days, 61 divided by 365, 4.8 years, according to this. Let me see, 125 times. Oh, that project cost is way too high. What is it?
So at 25,000, you're looking at for 26,000, you're looking at 4.7.
That you ought to be able to install that for $200 a horsepower. So 200 times 125, that's like 25,000.
Oh, 125,000 is different, I'm sorry. It's 150 per horsepower, I'm sorry. 125,000 is the another 5.
Yeah, so it's 25,000. 25 is probably reasonable. I was going to say that looked like a pretty bad payback. That's fine. There we go. 353 days. There you go. Cha-ching. Now we're in the money. Now everybody that hired you to come in the plant, they say, we knew that guy'd find us some good savings. They're all patting you on the back and going, yeah, we can take this to the boss and, you know, we'll get this done. And it's a good project. Absolutely. All right.
How do you get your internal
Internal rate of return? Yeah, let me. This is really good for, you know, I had a guy I do some work for DOE, and one of my handlers, that we go out to plants together, he threw this on me. You know, I mean, I didn't, 2-3 years ago, I didn't ever do this. And he just said, hey, I want you to put internal rate of return on this in your report. And I went, okay. How do you usually do that, Paul? He said, oh, you just go in Excel. There's a little calculator in there. Oh, thank you, Paul. I didn't know how to do it. Well, let me see here. Let me show you. I think I put a file in here just to be able to demonstrate that. How am I going to find it? Oh, Lordy. Maybe did I put it in the Steam system? I'll find it. Give me a second. I meant to demo that for you. Excel. ADM. Let's see. Where am I going to find it? Did I put it in Steam? I may have put it in Steam. Okay, just a second. Longevity. Here we go. Yes. Okay, so what you do, let's see, IRR. So internal rate of return. Okay, so there's the function. Can you see that? I can make it bigger, and then we'll have to look at these. Well, it's not getting bigger up here, but equal IRR, and then it's J14 through T14, 300. And let me, now do I, now I just have to remember. Okay, so this must be the, is this the, that must be the cost. Yeah, that's the cost. And these are the savings. This is annual savings, pretty sure. And so I think what you're supposed to do is run this out for the lifetime of the project. So say we're running 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're saying that this thing is going to for sure last 10 years. Every year it's going to save $11,779, and the initial cost is $20,000. Yeah, because see, here's 20,000, and here's IRR, and let's see. I'm not sure where the savings. I'm not sure where I came up with these numbers, but this is. I'm pretty sure that's how that works. But if you will, you can go on YouTube and Google Excel IRR function, and they will explain it to you better than I can. But
so he wants to consider a 10-year period?
Oh.
Because you're saying you calculate IRR for each.
That's a good question. That's a good question. Say, you know, when I give you this assignment, I see you as the highly paid consultant that comes into the plant. It's going to find them all this money. And then at the end of this, you're going to give them a bill for like $10,000. And you're going to give them a big fat report, which is based on your measure calculations and all of this ABB stuff and all of this. You're going to write that up into, you know, to justify a $10,000 bill, you're probably going to have to write them a 30 or 40-page report. And, yeah, and man, you're putting everything but the kitchen sink in there, you know, because you want that check, and you know you want to help them. And I mean, that's how the consultant world works. First, you got to gain their confidence. Then you got to get them to hire you. Then you got to get in the door, and you got to convince them that you halfway know what you're talking about. And then you find some stuff, you write it up, you send it to them. Hopefully they implement it and they're happy with you. And they call you up 2 weeks later and say, hey, that was so good. We want you to go to these 3 other plants. And you're sitting there and go, time to buy a new BMW. You know, life is good. So anyway, so this is my example on how to do it. It's not the best, but, and I think you can run this out as many years as you want to. And you simply have to tell it that range. Was it J14? Yeah, and the first one is the cost. And the rest of them, what's the 300? Oh, I think the 300 is an initial guess. Yeah, you have to give it some kind of an initial guess to get it started. Because I think it does some sort of an iterative thing where it actually calculates that. Yeah, it's all coming back now. It's probably been a year and a half, 2 years since I've actually used this thing. So anyway. What?
What is the guess for? What are you? What does that represent? What is 300 like? Yeah. Because you get a percentage out. What do you guess?
Oh, what is internal rate of return? Is that? I'm sorry, I can't hear you.
What's the 300?
That's an initial guess of the internal rate of return. The function has to have a starting place.
Okay.
So you have to put some kind of a number in there. You put 100, 200, something like that. It doesn't matter. You'll get the same answer. You can put 100 in there and you'll get the same, was it 58, 59%, whatever, yeah, 58%. That's the answer. But it has to have a starting to get the process started. You just give it a number that's anywhere close within a couple hundred and it'll, okay.
Just curious. I've never
Internal rate of return or return on investment. You'd have to look in your engineering econ. I can't remember. I mean, years ago, you used to have taken engineering econ class, and you spent a whole semester going through all those different things, and it's been too long. At one point, I was an econ major, and I'm embarrassed that I can't really answer that, but you just have to look it up. I don't remember. Okay, so these are my preliminary comments. Now it's time to get to the meat of the subject here, and we got to go back. Let's see. I know we did that. Condensing. I think we're right about here. Yeah, we're about to get rolling on condensing turbines. Okay, so this is what the power company does, and this is what we're going to have a hard time competing with them in most cases in an industrial setting. Condensing turbine discharge steam pressure less than atmospheric, so coming out of the low pressure turbine, we pull it down to 1 to 2 psi. Steam must be condensed because we got to get it back to the boiler, and we can't pump a vapor. Existing steam quality, or exiting, I'm sorry, steam quality is typically much greater than 90%. So between 90 and 95% of what comes out the end of that turbine is still vapor that still has roughly 1,000 BTUs a pound of energy. That's at 100, 110 degrees, and we're going to throw it away. That's the way it works. Primary factors influencing condensing turbine operation are purchase power cost, how expensive, purchase fuel, turbine efficiency, and to an extent, boiler efficiency and turbine discharge pressure. So, but those first three are the primary variables that influence it. So if you look at just the energy that enters the turbine, now we've said that of the energy that enters the boiler, roughly 50% of it gets thrown away in the condenser. But if we look at 100 units of thermal energy in the steam that's coming to the turbine itself, roughly 27 units of that get changed into shaft energy, and 73 units are in the exhaust steam, and that goes to the lake. So, wow. I mean, that kind of speaks for itself. Turbine receives superheated steam. In our example, 400 psig and 700. Isentropic efficiency here, big turbine, assumed to be 80%, and the discharge condenser pressure, 1.4 psi. That was the basis of these calculations. If you look at the performance, it's much harder to make money with a condensing turbine. And it's because of all the throwaway of the energy. The back pressure turbine, we assume that we're going to take all of that energy exiting and use it in the plant. So, I mean, what the heck? We're putting in a little extra in the boiler, and we take out a little in the back pressure turbine, and we still use the rest of it. Much more efficient mode of operation. So here on this chart, we have to include the isentropic efficiency of the turbine. We got the fuel cost, and this is the impact power cost in dollars per megawatt hour. So you got to move the decimal point 3 places to get dollars per kilowatt hour, which is what we probably think in more. Big guys thinking, you know, TVAs of the world, it's dollars per megawatt. You know, the big boys thinking dollars per megawatt. People at home and, you know, smaller businesses is dollars per kilowatt hour. But so at 40% isentropic efficiency, $2 fuel, we're looking at what, 5.6 cents a kilowatt hour. Well, crap. I mean, that's, you know, at 80% isentropic efficiency, $2 fuel, we're looking at 3 cents a kilowatt hour. And man, I mean, that's about as good as it's going to get. You're probably not going to have $2 fuel, and you may not have 80% isentropic efficiency. So if we get down to something like, say, $8 fuel at 60%, we're looking at what, 15.5 cents is our cost to produce it. Oh, crap. Only part of that. I can buy it for 7 or 8 from the utility company. So you see, whereas the back pressure turbine economics were compelling, these are compelling in a reverse direction for most cases. Now, I have seen industries that were in a situation where they were going to have to vent steam, or they were going to have to throw energy away regardless. And so some of them run condensing turbines because at least they get something out of it before they throw it away. But generally speaking, if you're buying fuel to make steam, to put it into a condensing turbine, and you're trying to compete with a power company, you're going to lose. Unless, if you got free fuel, okay, you can probably make that work. But if you got to buy your fuel at much of any kind of a cost, you can't compete with them. Utility company's too good. But if you can do it with a back pressure turbine, you can kick their tails all day long because you utilize the energy out of the turbine, whereas they throw it away. That's kind of the game. Okay, efficiency reductions on turbines can come from blade deposits, blade erosion. Those pictures I had last time, you could see some erosion on the back of the turbine blades. We can get blade deposits. I've got some pictures of those. Seals, the steam can leak. Instead of going through the blades, they can leak around the blades, in which case you get nothing out of it. Wet steam, too many water droplets in the steam can erode the turbine blades and cause damage. And throttling depends on how your control valves are set up. If you use throttling type control valves to control the amount of steam that goes through, there can be losses associated with those. Efficiency improvements can result from, we could reblade. The blades could be damaged, or ever so often, sometimes they can come up with a better design on the blades that is a little more efficient, and you could get more power out. Improve seals to reduce the leakage. You can replace the whole turbine or increase load. At close and at rated loads, these things have better efficiencies. Okay, these are some pictures. This is from Jamaica. Jamaica Mon. This was Jamalco. This is a big, it was an Alcoa bauxite refinery. And that's about a 32 megawatt back pressure turbine. Look at the crud on the blades. That is silica. Silica carries over in steam. So what these guys were doing is a lot of hot water comes out of the process, and they bring that water back, and they purify it the best they can, and they put it in their boiler. But that water comes back loaded with silica, and they couldn't remove all of it. And so then they make the steam, and silica is one of the few things that carries over in steam. So the silica rides with the steam through the turbine, and guess where it winds up? On the turbine blades. What kind of isentropic efficiency do you think those blades had? Not very good. So what happens is they have to clean this turbine every 5 to 7 years. And silica is hard to get off. You have to sandblast it off of there. So electricity in Jamaica costs 26.5 cents a kilowatt hour. 26.5 cents. And this thing is making 30 megawatts. What's that worth a year? 30 megawatts. $30,000 kW times, let's just say 8,000 hours times 26.5. That's too much. Just a second. That's too much. That's way too much. That's more than the national debt. 30 megawatts times 8,000 megawatt hours per year times, 26.5. That's about $6.4 million divided by 12. So for every month this thing was down, it would cost the plant $500,000 in additional electrical purchase. It's at least a month, if not longer, to take that thing apart and sandblast it and get it all cleaned up and put back together, all the maintenance done. You can see why they were not particularly anxious to tear it down. But what happened is when it was clean, they'd get 30, 31 megawatts out of it. Well, 2 years later, they're getting 29 megawatts out. 2 years after that, they're getting 26.5 megawatts out. A couple of years after that, they're getting 22, 23 megawatts. When it gets under 20, the loss in power is so expensive that they just say, we have to. We have to take it down, take it apart. They have people come in from Europe to clean the thing. I mean, it's a big, and it's $1 million project to clean it. So silica carry over in the water. So we did a lot of research into technologies to remove silica. And there were, I can't remember all the details, there are some technologies that were on the market that would potentially remove a lot more of the silica from their boiler feed water. That would help. I don't know if it would eliminate, but it would certainly slow down the accumulation of this stuff on the blades. Whether they ever did it or not, I don't know. But I could pull up the final report and take a look on what we finally recommended for them. But anyway, that's pretty interesting. And see up here, you see these seals up here. See, there's a stationary. I mean, the turbines open up, but there's a whole row of stationary blades, and then these are the rotating blades in the rotor. And see these little sealing strips up here? This is seals, because if those things get damaged, then instead of going through the blades, the steam can come up around and just go around the stage instead of through the stage. And obviously then that's a leakage path that hurts you. Okay, condenser pressure can be reduced. So if we can get the back pressure down lower, we have a bigger delta P, we get more power out. Well, one thing that happens is that we get non-condensable gases. You get some air, you get some nitrogen, you get some other stuff that gets down there in that condenser, and then all the steam comes in, you got extra gas down there, the back pressure goes up. So these condensers are built with air purge systems that can distinguish between steam and air and gases, and they're supposed to keep that stuff pumped out of there. But they don't always work right. You know, something could be down, there could be extra air leakage into the system. Because this stuff is 1 to 2 psi, you got 14.7 psi atmospheric pressure, so that air is constantly trying to leak in. And you got a 10, 12 pound pressure difference pushing on it. You get deposits, you can clean it. Reduced temperature water, that's pretty tough, you know. The old joke is, what, you gonna dump blocks of ice in Watts Bar Lake to cool down the lake water that goes in to cool the power plant? Probably not. So, I mean, you know, it might be possible to pull the water from deeper in a lake or something where you get colder temperatures, but then you get too close to the bottom and you suck all the mud in. So you got to be careful with that. Or sometimes now that last bullet, pumps degrade and your pumps may not be pushing the rated flow. So you can try to take flow measurements on the pumps and make sure that they're up to speed. If they're damaged, then less cooling water, higher back pressure, less power, the way it works. Okay, let's look at distribution system losses a little bit. Steam leaks, pipe failures, and trap failures. Okay, steam leaks. Some of these plants, especially in Brazil, outside the country, you go in, you walk, they got all this processing equipment, and you walk around, and there's just little puffs of steam. Every once in a while, there's a bunch of steam. A valve, you know, a crane hits something, and a lot of times they can't fix it until they take the process down. And they don't take the process down but every 6 months. So they just walk by and go, well, you know, I'd fix it if I could, but I can't, so I won't, you know. That's management's problem. I can't help it, you know. I wasn't driving the crane, and you go on. But we can have steam traps open, blown gaskets, damaged pipes and fitting. So you walk up and you see something like this. So see, the valve handle is perpendicular to the valve, but it's leaking through. So it's failed. Well, I mean, how do you estimate? How much is that? Is that 10 pounds an hour? Is that 100 pounds an hour? Is that 1,000 pounds an hour? You know, you're out surveying a site, you walk up, take a picture of it for sure, figure out where you are, write it down on the list, you kind of go, small, medium, large, extra small. How this game gets played. Now this one, actually, you have an orifice there. So you might actually be able to do a calculation. If you know the upstream pressure, you know it's atmosphere on the other side, but you're not really, I mean, that thing is probably not just a clear, wide open path through that. You know, something's failed in there and you don't know what it looks like on the inside. So all you can do is look what's coming out. If you're doing compressed air, we have a thing on something like that called the bag test, where we carry a garbage bag with us, like a 30-gallon garbage bag. And you reach down there and you're somebody with a stopwatch and you reach around there and you clamp it with your hand and you hold it. Somebody starts the timer on his watch and you see how long it takes the bag to inflate. So you know cubic feet per second, per minute. So you know the leak rate. It's kind of hard to do on steam. And steam hits that garbage bag and poof, it's gone. You know, you might not have any gloves good enough to hold on that thing. So we don't really do that on steam, but we do it on compressed air. So how would you estimate? I mean, you just do the best you can. This is more like what you see. You got a valve and you got gaskets and all that stuff and it's just spewing out. But you know, you look at this one and you go, well, you know, that's pretty small. You look at this one and go, oh, that's a little more. At some point, you have to put a number on it. Okay, this is Napier's equation, and this is in that steam system survey guide that you all have. I think it's chapter 5, and it gives this equation. And this could be used. This could be used on the homework. Or we also have leak tables. We have some that are in here. And there's others you can find online. But to use this, you've got that constant 5143, and it's just multiplied by the cross-sectional area of the orifice in inches squared times the steam pressure in PSI-A. Okay, now catch this. So where this stuff is developed is like in laboratory testing. And so when you make an orifice, you know, you go in the shop, take a plate, drill a hole in it. Well, you can have a sharp-edged orifice, and you can have a dull-edged orifice. So a sharp-edged orifice, I guess because you have more turbulence around that sharp edge, will pass roughly 60% of what a dull-edged orifice will pass, based on scientific testing. Oh, that's great. So I look at that, and I go, is that's 3/8 of an inch dull-edged orifice. The next guy comes by, no, that's 1/4 inch sharp-edged orifice. The next guy comes by and says, oh, that's 1/2 inch. I mean, you know, you don't know. It's an order of magnitude guess. Now, the more of these things that you look at, the more arrogant you get about thinking that you know what you're doing. Well, I've looked at a lot of these, say, oh, that's 1/4 inch. That's 1/4 inch dull. Guy writes it down. You go back and do the calculation. Does it make it right? No. Just when you present it, you have a lot of confidence. You go, oh yeah, I've seen, you know, I've been in 52 steam plants, you know, and I'm pretty good at this stuff. Don't forget to pay me. So anyway, but I mean, you know, between, that's not 5,000 pounds an hour. I mean, 5,000 pounds an hour is probably what comes out of a 2-inch pipe, just, you know it's not that. On the other side of things, you look at a 1/16 of an inch, it's probably 2 or 3 pounds an hour. You go, well, that's not that either. So you just start kind of chomping it down until you go, okay, I can live with this. And that's what you calculate. Because very, very rarely does anybody have a steam flow meter that is just going to pick up, you know, leak in one pipe. You know, they might have one in the boiler house, but it sees everything. So that's not a whole lot of use to you most of the time. Okay, blowing steam trap, determine trap size, which I gave you, and use that along with steam pressure to estimate loss rate. steam leak, make a judgment, then estimate the loss rate. Okay, some other stuff. Systems get taken down for maintenance, outage. A lot of times the steam system, the boilers are shut off, opened up, stuff done. All the pipes, everything cools down, and then it may sit there for a week or 2 weeks, and then they heat it up and they bring it back up. And all of this stuff expands and contracts when hot. All your gaskets, all your flanges, all this stuff. If you've been out for a week or two and you come back and heat it up, you're going to find leaks. They're going to happen. You know, it's possible that you could, you know, have a fatigue crack in an elbow or a fitting or something. It's more likely that a gasket or something, just the expansion contraction, you got a crack someplace that you didn't have one before. This shows a leak table. This is pretty typical. And you see this one has this discharge coefficient of 0.6 built into it. So this is for a sharp-edged orifice. If you thought you had a round-edged orifice, you would divide these numbers by 0.6. Yes, sir.
So, as far as the area of the orifice calculation, are we using this like a standard, like perfectly round circle, or like what are we using?
No, it's just, I mean, an orifice, but it's typically, it's just a round hole.
So we just use
Yeah.
pi r squared.
Yeah, exactly. It's just a round hole. Because see, that's the only way that they can test these things. Because, you know, I mean, you can go find a cracked fitting or valve and take it in a lab and test it and get a flow rate, but then what do you quantify that to? Oh, it's a 2-inch valve and the gasket's half gone, and I mean, you know, so the only way that we really have to do this is to go in, you know, to a laboratory and make a bunch of orifice plates or buy them that have, you know, a 1/4 inch hole, 3/8 of an inch hole, 1/2 inch hole, 1/16 of an inch hole, you know, whatever we got over here, and set those up in a highly instrumented system and measure the flow rate through them. And then, so we have some degree of confidence in this. The problem is when you go out in the field, your leak is not an orifice with a hole in it. So you have to somehow make a judgment call. This leak in the field is equivalent to a 3/16 diameter, and I know my pressures. Now, usually I know my steam pressures. I can get a pressure measurement.
The reason I'm asking is because I took that Nepier's equation, and instead of doing 51.43, I did 60 for the 60%. And at 400 psi, which in Nepier's equation you use PSIA, so you have 14.7, and 1/4 inch, which is what we were given in the Word document. If you do the pi r squared for area, the numbers don't match the table.
Well, send me an email with what you calculated in there, or just give me a copy of it, and I'll take a look. This table's correct.
Oh, yeah, that's what I'm saying. So what I did was I worked backwards.
Yeah, I understand. Well, there's probably, no, I mean, these involve the actual area. I mean, it's just, there's a difference in interpretation someplace. So. Okay, well, as much as I'd like to go ahead and blitz through this thing, I'm sure everybody at home is already sound asleep on their couches. Wake up now, wake up out there. And we will, this is Thursday, so be working on this. If you have questions, email me. I'll get back to you as quick as I can. And we will convene again on Tuesday. Everybody have a great weekend and be safe.